When the Voyager 1 probe crossed the invisible boundary at the edge of our solar system, its instruments registered a physical anomaly. The environment outside the spacecraft was thickening. Specifically, the plasma density, the concentration of charged particles in space, was steadily rising. As we see in this model, our sun constantly spews out a stream of charged particles called the solar wind. This creates a massive protective bubble around our planets known as the heliosphere. But the void outside this bubble is filled with cold plasma, gas, and dust left over from ancient supernova explosions. Right here at this border, known as the heliopause, the solar wind pushes outward from the inside, while the interstellar plasma pushes inward from the outside. They crash into each other, creating a turbulent wall where the particle density spikes. Today, both Voyager 1 and its twin, Voyager 2, have breached this barrier and are cruising through the cold expanse between the stars. We are currently receiving real-time data from them, tracking the composition of this interstellar medium right this very second. To understand how we are still hearing them, we have to look at the hardware. This is the Voyager spacecraft, built with technology from the mid-1970s. Since launching in 1977, these probes have traveled tens of billions of kilometers. The combined random access memory of all 6 computers on board each probe is exactly 68 kilobytes. For context, the microchip inside a modern electronic car key is more powerful. All the scientific data they collect is recorded onto a vintage 8-track digital tape. When it comes time to transmit that data back home, the spacecraft uses a radio transmitter with a power output of roughly 20 watts. That is the same amount of energy used by the small light bulb inside your refrigerator. Look at how this transmission behaves over time. A radio signal traveling at the speed of light takes 22 hours to cross this abyss. As the radio wave spreads out, its power drops to less than 1/billionth of a watt by the time it reaches Earth. To pluck that at-a-watt whisper out of the static of the deep universe, NASA uses a series of precision filters designed to overcome the physical interference of motion and heat. The probes only reached this distance thanks to a rare quirk of orbital mechanics. In the late 1970s, the outer planets aligned in a configuration that occurs once every 176 years. By using the gravity of each planet to slingshot the probes forward, NASA cut the travel time to Neptune from 30 years down to just 12. This image of Jupiter was captured during that high-speed grand tour. Voyager 1 revealed an atmosphere driven by high-speed jet streams and storms, while discovering active bluish volcanic plumes erupting from the moon Io. The probes then reached Saturn, capturing this intricate system of hundreds of rings. This was their final shared milestone. Voyager 1 was steered close to the moon Titan, where gravity flung the probe up and out of the planetary plane into deep space. Out in the dark, the sun is nothing more than a bright star, which makes solar panels useless. Instead, the probes survive using radioisotope thermoelectric generators. Inside a durable capsule, a pellet of plutonium-238 naturally decays, generating heat. Thermocouple plates convert the temperature difference between that hot plutonium and the freezing vacuum of space directly into an electric current. But plutonium-238 has a half-life of 88 years. Every year, it releases less heat, and the generators produce less electricity. To compensate for this decay, NASA engineers perform remote triage. They systematically shut down scientific instruments, sensors, and even internal heaters, sacrificing parts of the machine to keep the core alive. The Voyager mission has become a meticulously managed, slow-motion battle against thermodynamic decay. To receive data from that decaying power source, you need hardware built on a planetary scale. This is one of the massive 70-meter antenna dishes that make up NASA's deep space network, the physical net designed to catch that at-a-watt signal. The first requirement for these dishes is total geographic isolation. They are built in the remote deserts of California, Spain, and Australia. If they were anywhere near human civilization, the signals from our cell towers and satellites would drown out Voyager entirely. The second requirement is hyperdirectional targeting. To ignore the radiation from billions of other stars and galaxies, the antenna focuses on a mathematically exact microscopic patch of space, physically ignoring the rest of the sky. But size and placement are merely the prerequisites. Actually extracting the data requires actively fighting the physics of motion and heat. Here is the first problem. The Doppler effect. Because the spacecraft is moving away from Earth at blistering speeds, its radio waves physically stretch out, shifting the frequency downward. NASA computers calculate this stretching in real time, constantly retuning receivers to catch the shifting pitch. Once you capture that shifted wave, a more insidious barrier remains. The receivers here on Earth are made of metal, and the random motion of electrons inside that metal generates heat. That internal thermal hum creates enough white noise to instantly crush Voyager's cleaned-up signal. To stop those electrons from vibrating, engineers cryogenically cool the most sensitive components of the receivers down to near absolute zero, minus 273 degrees Celsius. This freezes the thermal motion in the metal, creating an environment quiet enough to detect the incoming data. We can only receive the faint, decaying warmth of a 1970s machine by artificially constructing the coldest environment possible here on Earth. Engineering can filter the noise, but it cannot reverse the atomic decay of the plutonium on board. Sometime in the early 2030s, the physical power reserves inside both probes will drop below the minimum required to keep even a 20-watt transmitter running. Earth engineers will format one final sequence of code and transmit a command to power down. That signal will travel for 22 hours, hit the spacecraft, and execute. After that, there will be permanent silence. This loss of signal marks the end of their utility as scientific instruments and the true beginning of their endless voyage through time. Bolted directly to the side of each spacecraft is the golden record. It is a physical payload designed specifically for the era of silence. It is a gold-plated copper disc carrying the sounds of Earth's music, photographs, and greetings in dozens of languages. Engraved on the aluminum cover is a map pinpointing our planet's location. In 300 years, the unpowered probes will drift into the inner edge of the Oort cloud, a shell of icy bodies surrounding our solar system. They will spend 30,000 years crossing through it. In 40,000 years, they will make their first close passes by entirely different star systems. As you see here, in roughly 5 billion years, our sun will swell into a red giant and scorch the Earth into a dead cinder. By that time, the Milky Way and Andromeda galaxies will likely begin to collide, rearranging the orbits of billions of stars. The Voyagers will sail through that chaos. Long after the Earth is gone, these two battered pieces of metal will drift through the darkness until the decay of matter itself. They will remain as humanity's final proof that somewhere in the universe, life looked up and reached for the stars.